Hello and good evening. Welcome to our fifth week lectures in our series of lectures on statistics for the social sciences. As usual, Amos Peter is my name, and I welcome you to this lecture. And today, we shall be talking about a very important statistical concept, and that is samples and populations. And permit me to share the course outline with you. So we shall talk about populations and samples, even though in the first lecture, I still talk a little about population and samples, but today's topic is mainly dedicated on populations and samples. So we shall see what a finite population is and what an infinite population is. Then we shall talk about what is sample, and then the different types of sampling. And then we shall also talk about sampling error and how to calculate or determine a sample size whenever you want to carry out an experiment or a study. And basically, what is a population? In statistical analysis or any experiment or study that you want to carry, a population is a term that is given to the entire set of information, individuals, objects, or measurements with a common and observable characteristics in a defined environment at a given time. In other words, a population is the superset on the study. A typical example is when you want to carry out a study about the performance of students at UTEL University. Now, the entire student enrolled at UTEL University is referred to as the population of study. Another example of population is if you want to carry out a study about or on post-traumatic stress disorder on the military personnel in the Mexican army, then of course the entire number of people or personnel that are serving in the Mexican army, forms what we call your population. So population is the group actually from which sample is drawn. Now, the reason why in most cases we don't want to deal with population is because of the fact that we do not always have the time and enough resources to carry out any study covering the entire population. So rather, what we do is that we take a little portion out of the population, and that little portion that is taken out of the population is what is referred to as a sample, as you can see depicted in this diagram on the right-hand side of this PowerPoint slide. So you can see that the entire entity or people or object forms the population, while out of the population, we decided to take a little subset as shown in this white, cycle, and then pull out that forms what we call a sample. And that's why you can see here, I said a sample is a small group of members selected from a population to represent the population. A sample can also be seen as a faithful and representative subset of the population. Now, it is important to note that while taking out sample, that the sample must be the majority, and it must represent the others that makes up the population. And you have to try as much as possible that when you are taking out sample, you do in such a way in order to minimize bias. In other words, the sample must be uninclusive and a true representation of your entire population in order to get a correct and meaningful estimate of your statistical data. Now, before we proceed, permit me to share the first open class question. And the first open class question says, write about the factors to be considered before sampling. In this assignment, I want you to use not more than a page, either a 1 or 2 paragraph, to highlight some of the factors that statisticians or researchers need to consider before carrying out sampling. Now, having defined what population and what samples are, let's now see what is sampling. Now, sampling is a verb as opposed to samples, which is a noun. So in other words, a verb is an action word or a doing word. So sampling, in this case, is a process or an activity used in statistical analysis in which a predetermined number of observations or items or objects are taken from a larger population. So the process or the activity of actually picking out individuals or objects or entities from an entire population, which is going to serve as the basis of a statistical study or research, is what is referred to as sampling. It is important to know that sampling is a method that allows researchers to infer information, in other words, to draw conclusions and make inferences about a population based on results from the sample. Now, the methodology used to sample from a larger population actually depends on the type of analysis being performed. As we shall soon see, there are various methods or ways in which you can carry out the sampling. And it's actually a function of the types of study that you intend to carry. And here, I just decided to highlight, even though I've mentioned them before, some of the advantages of using samples. This helps us to incur lower or fewer cost. And of course, we take lesser amount of time to study samples than to study entire population. And of course, we make use of less resources. Now here, let's discuss the different types of population. Since we say that the population is the entire item or data of interest or the superset from which samples are being drawn. So let's see the different types of populations that we have. Basically, populations can be broadly classified into what we call a finite population and infinite population. And what do we mean by a finite population and an infinite population? Of course, as the word implies, finite, it's something that has a definitive count that we can count, and it has an ending. So finite population, these are populations that have a known size, e.g. the number of students in a university or the number of personnel, like I said, military personnel serving in the Mexican army. Of course, at any time T, you want to know, the Ministry of Defense or the registrar of the university can always give you those numbers because the number of students or personnel can actually be counted. So we see such kind of populations from what we call a finite population because they have a known size. Now, in the case of infinite population, as opposed to finite population, infinite population, you look at the word infinite gotten from the word infinity, which is actually a mathematical abstract construct to show something that is larger than what we can actually count, something that has no end. In other words, it has no known size. Now, here we say that these are populations that have uncountable amount of elements, or those that are finite but very large. And an example is the number of people in a continent, let's say Africa or South America. Even though it actually would be possible to count the number of people on the continent, that is going to require a very huge amount of resources and, of course, a very large amount of time for such kind of census to be conducted. Another example of infinite population is the number of stars in the universe. It will virtually be impossible to count exactly the number of stars. And even astronomers simply just make an intelligent guess in such cases. Another example of an infinite population is the number of sands in the seashore. That is virtually impossible to calculate or to count. So these are the two broad categories in which populations are being classified or grouped. Now, having seen the different types of population, let's now see the different types of sampling methods that can be carried out during research or experiment. Now, the first category or type of sampling is what is referred to as the probabilistic sampling. And of course, this is gotten from the word probability. And in probabilistic sampling, this is a sampling methodology that is based on the fact that every member of a population has a known and equal chance of being selected. For example, flipping a coin or throwing a dice. In the case of flipping a coin, you know that, of course, that a coin can either have fall with head or with tail. And you can see that the probability of the chance of a head turning out is actually 50%, while that of a tail turning out is also 50%. While in the case of the dice with 6 faces, they all have equal probability of 1 out of 6. So for any kind of sampling methodology that does the sampling in such a way that the members of the population can have equal chances of being selected without any bias is known as probabilistic sampling. While in the case of the non-probabilistic sampling, it's a sampling that does not involve a fair chance. So this involves a non-random selection based on convenience and other criteria, as we shall see in the course of our study. Now, here, I want us to quickly see under the probabilistic sampling, what are some of the different methods that falls under the probabilistic sampling. Now, the first type of sampling methodology under the probabilistic sampling is what is referred to as the simple random sampling. The simple random sampling. And of course, the simple random sampling is exactly what I've explained earlier. It's a kind of sampling method that is carried out in such a way that every member of the population has equal chance of being selected. Now, we want to give an example. Suppose you have 30 students in a class. 30 students in a class, and you intend to select 15 students to form a team that will play a particular game. Now, a simple way of doing this using a simple random sampling is for you to get small pieces of paper where you write the names, either the names of all the 30 students, or you write selected in some of the, let's say in 15 of the small pieces of paper, and not selected in another 15 small piece of paper. And then, of course, you fold the paper and then put all the papers in a bowl. You put all the 30 pieces of paper in a bowl, and then you shuffle the paper in such a way that they are completely mixed up. And then you ask each of the students to come and dip his or her hand into the bowl. So if a student picked a paper that is marked as S, it means he has been selected. For those students that pick a paper that is marked as N, means they have not been selected. So this is a simple random sampling that ensures that all the members in the population have equal and fair chance of being selected. Now, the second type of sampling is what is referred to as systematic random sampling. Now, I want us to take note of the word systematic because it actually follows a system. It's also a random sampling, but it has a system. Now, in this kind of sampling methodology, samples are selected actually as specific or fixed intervals. But actually, what you will do is that, for example, you could have a random, okay, for example, let's still use the case of the static student. And you want to select, let's say, 5 students or 6 students. Now you could decide to have a random number generator that may generate the first number for you. And then maybe if, let's say, the number 3 appears, And let's assume that these students are actually lined up. So supposing the random number generator throw up 3, it then means you start with the third student. And then you will now begin to sample at specify or fixed interval. So you will not pick another student until after the third student again. So it means you count 1, 2, 3. So in this case, you pick this is the third, fourth, fifth, sixth student. Then it means the next ninth student will also be picked until you have all the 6 number of students that you require in your population. So this is called a systematic random sampling because it follows a system. So every nth or kth student will always be selected at a specific interval of 3, 3. Now, the third types of probabilistic sampling is what we refer to as the stratified sampling. Stratified sampling. Now, stratified sampling is gotten from the word strata. In other words, your strata or groups. In other words, in stratified sampling, the items or the population of interest are actually divided into groups or strata based on certain criteria. So, for example, you could decide if you want to conduct a study about the prevalence of a certain kind of disease, let's say prevalent in a particular city, you could decide to form different groups or strata of, let's say, young people or teenagers, if you wish. Then you also have another strata, let's say, of adult. And then you could have another group or strata, let's say the aged or the old people. And then from each of these group or strata, certain numbers of people will then be selected in order to carry out the research study. Now, the last but not the least type of sampling is referred to as the clustered sampling. Clustered sampling, or we also call it the conglomerate sampling. Clustered or conglomerate sampling. Now, in this type of sampling, usually a group of similar things or people are usually formed. A typical example is if you want to carry out a market survey about how a certain food item or product is faring in the market. You could decide to divide the city or the country into different clusters, such as Northwest, Southwest, Northeast, and so on and so forth. And basically, or you could also decide to divide the groups in, on the basis of zip codes, or the city on the basis of zip codes. And having divided the city on the basis of zip codes, you then randomly select some of the groups. Randomly select some of the groups, not all of the groups, and then you sample everyone in the group. So that is that about clustered sampling. Now let's see the different types of non-probabilistic sampling. The first type of non-probabilistic sampling is what we call the intentional sampling. Intentional sampling, or sometimes we call it convenience sampling. And as the name implies, it is a kind of sampling in which the researcher makes use of data that is readily available. And for example, you want to carry out a study about people's opinion concerning a particular TV program. You could decide based on convenience to just sample your friends. But however, we should be careful that some of this kind of sampling will actually have their own drawbacks, because sampling your friends may not be able to give a true representation of what the entire population or the people in the city perceive, concerning the program that you want to get opinion on. So it's an intentional sampling is simply sampling based on convenience. And this is because maybe the people under study or the items or population under study can be easily accessed by you. So you just decide to make use of those population for the study. And then the second type of non-probabilistic sampling is known as quota sampling. We have quota sampling. And in the case of quota sampling, as the name implies, you simply divide the population into groups, various different groups, and then you allocate each of these groups a certain quota. Maybe you say group A will give us 20%, group B 20%, and up to group 5, 20% to form a total of 100. Now, the third but not the least type of non-probabilistic sampling is not what we call the snowball. The snowball sampling, and sometimes it's also referred to as network sampling. Now, in this type of sampling, basically, when you sample, usually you start by picking one sample in the population, and then you ask that very particular sample to refer you to the next, sampled to be questioned. And then the second also refer you to the third, and so on and so forth. So that is why it is known as a network sampling. Now let's make progress. Now here we're going to talk about sampling error. Now remember, I told you that sample is typically only a part of the whole population. So because of that, since sample is just a subset of your whole population, it is worthy to note that sample data actually provides us only a limited information about the population. So as a result, sample statistics are generally imperfect representative of the corresponding population parameters. So that is why when we want to sample, we need to try as much as possible to ensure that we sample properly so that we can minimize this kind of discrepancies. Now, the discrepancy or the difference between a sample statistic and its population parameter is actually what is referred to as a sampling error. And it is the goal of the researcher to try and minimize this error as much as possible. And defining and measuring sampling error happens to be a very large part of inferential statistics. Otherwise, you may not have a true representation of your population parameter. Now, this slide is just trying to give us an idea of what sampling error is. You can see in the first cycle here, we have a population of 1,000 college students. And statistical tools or analysis were applied on these 1,000 students in order to get some important statistical measure. So you will see here that the average age of this 1,000 college student happens to be 21.3 years. The average IQ of the 1,000 student is 112.5. And this 1,000 student, we have 65% of the students to be female and 35% are male. In other words, it means 650 are female and 350 are male. And then out of this 1,000, we decided to draw samples, random samples of 5 students each. And then the same statistical, the same statistical indices were calculated. So in this case, here we have Eric, Jessica, Laura, Karen, and Brian. And then these are the sample statistics as opposed to the population parameter. The average age of these 5 students happens to be 19.8. The average IQ is 104.6. And here we have 60% female and 40% female. You can see that in this case, for the population parameter, the average age is 21.3, while here is 19.8. So usually you see you have 21.3 for the population, and then you have 19.8 for the sample. Now, basically, the difference between these 2 digits, that's for the population parameter, and the sample is actually what is referred to as our sampling error. So if you minus subtract 19.8 from that, from 21.3, you have 1.5. So it means we have 1.5 as the discrepancy. That's the discrepancy. So that happens to be our error. So, and it is important that we try as much as possible to minimize this error. The same applies here. You can see for this 5 set of students, the average age is 20.4. So if you subtract 20.4 from 21.3, that gives you the error, and so on and so forth. So we shall see in the subsequent slide how we can calculate all this sampling error under 3 different sets of conditions. In other words, we are going to see how we can calculate the sampling error for an infinite population, and we'll also calculate the sampling error for a finite population, and we'll calculate the sampling error for a whole population. And in all these calculations, we shall be using the same set of data, or the same question, though framed differently. Now, generally, once we take a sample, we actually want to have, or we have 3 questions in mind that we want to investigate. In other words, what is our best estimate of the population mean? You see, we have a sample, and we want to make use of the sample in order to draw conclusions or inference or make projections concerning the population. So we want to see what is our best estimate of the population mean. The second question is, having gotten our population mean, we also want to know how confident are we about this estimate, whether this estimate is a true or a fair representation of our population mean. And then the third question is, what is our best estimate of the population standard deviation? Now let's make progress and see. And before we continue, permit me also at this point to pose the second open class question, which says simple random sampling can be drawn with the help of A, random number table, the cheat method, the roulette wheel, D, all of the above. So it's just a matter of you selecting the right option. Now let's see proper how to calculate the sampling error using this question that we are going to ask. The first example says, estimate the height of basketballers from the following sample. Now, it is important for us to take note of how the question is being framed. This question happens to be an open-ended question because it says estimate the height of basketballers. It did not tell us which basketballers, in which team, or in which country. Probably we have been asked to estimate the height of basketballers in the whole world. So you can see that this happens to be an infinite population because it simply says estimate the height of basketballers from the following sample. So in other words, you are just given a few sample of 5 basketballers, and you are being asked to estimate the height of basketballers, and you are not told basketballers in a particular or specific team. So in this case, we'll assume that is the whole basketballers in the whole world. So in this case, we need to, what are some of our data that we need to take out, the variables that we've been given? So we are given 5 samples. So in other words, it means we have our n is equals to 5. Now, the first thing we want to do, just like I told us from the previous slides, whenever we take samples, we want to see what is our best estimate of population mean, and then how confident are we about the estimate, and what's our best estimate of the population standard deviation. So in this case, we are given that our sample n is equals to 5. So for us to get our sample mean, which is being represented by x bar, we can get it from this formula, which we already knew in our third lecture when we talked about measures of central tendency. So it's the sum of x, sum of x so it's the sum of x divided by n. And in this case, the sum of x simply means the summation of all these numbers, this height. So you add 1.98 meters plus 2.03 meters plus 2.08 meters plus 2.16 meters plus 1.88 meters. And if you do the math and then you divide that sum of this height by 5, you should arrive at this, that the mean is equals to 2.026 meters. So in other words, this is a sample mean. Now, having gotten this, then comes the second question. Or rather, it means that this is our best estimate of the population mean. So in other words, this is our best estimate of the mean height of all the basketballers in the world. Now, the next question is that we now want to ask, now, how confident are we? How confident are we that the population mean height of basketballers is 2.026 meters. So we want to know how confident are we that this 2.026 meters is the mean height of the basketballers in the world. And usually we do that by calculating the standard error. So we do that. Calculating the standard error, and the standard error is being calculated as standard error of the mean height is being given as S divided by the square root of n, where this S stands for standard deviation. Standard deviation, and then n is the sample size. So, and how do you calculate the standard deviation? We've done that when in our fourth lecture, when we are calculating measures of dispersion. So standard deviation, we already know, is given us with this formula, which is the sum of x minus x bar squared divided by n minus 1. And of course, if you do the maths, you should have that your standard deviation is 0.1053 meters. So this implies now that since we've gotten our standard deviation, this implies that our standard mean error is going to be equals to the standard deviation, which is 0.1053 divided by the square root of n, and our n is 5. And calculating that gives us a standard error of 0.0471 meter. Now, it is important to note that the higher the sample error, this implies that your mean is not a true representation of your population mean. So you can see we've gotten a standard error of 0.047. Now let's see how we can also calculate the standard error, but in this case for a finite population. Now the question says, estimate the average height of all 1992/93 Chicago Bulls player from the following sample of 5 players. You can see that it is still the same question, but the question has been framed slightly differently, because here it is talking about the Chicago Bulls players, the Chicago Bulls players or Chicago Bulls team, but we want to estimate the mean height of all the players in the Chicago Bulls team, but from the height of only 5 players. So you can see in this case, we equally have that our n is equals to 5 as before. And our n, the whole players in the team, happens to be 14. We know that players in a basketball team are usually 14. So in this case, now let's calculate our sample mean. Our sample mean, x bar, is still giving us the sum of x divided by n. So this implies that if you do the maths, you also have x bar is equals to 2.026 meters as before. Now, in this case also, how confident are we that the population mean of basketballers is 2.026? We also do that by calculating our standard error, and we calculate our standard error in this case using this formula that's for a finite population. Is giving us S divided by the root of n multiplied by the root of capital N minus small n divided by capital n minus 1. Now, where S, as usual, is our standard deviation, which is also gotten from S, standard deviation giving us the sum of x minus x bar squared all over n minus 1. And if you do the maths, you should find that your standard deviation is equal to 0.1053 meters. Now, our standard error then is going to be equals to, we simply plugged all this data into this equation here. So our standard deviation, we've gotten as 0.105 divided by the square root of 5 multiplied by the square root of n. Capital N is 14 minus 5, that gives us 9, divided by 14 minus 1, that gives us 13. And if you do the maths, you should have that your standard error is 0.0391 meter. Now, I want you to take note that in the case of the standard error for the infinite population is 0.047 meter, while in the case of a finite population is 0.0391 meters. You can see that because we have a finite population, at least a population that we can count and that we know the size, you see that it gives us a slightly lower error as compared to an infinite population, because an infinite population contains a very large amount of items or members in that population, of which you are only given a small sample of 5. So you can see that the more you know the population and the proper representation of samples you pick, the more accurate your sample mean is going to be, and the less the error you're going to make. And let's see how to calculate the sample error for a whole population. Now here it says, what is the average height of all 1992/93 Chicago Bulls starting 5? So the height of Chicago Bulls starting 5 are given. And in this case, our population of interest, we are only interested in the starting 5 of the player. So you can see that our population of interest P is equals to 5. And also our sample of interest is the same thing. Our sample of interest N is also equals to 5, because we are only given a population of 5 and a sample of 5, but from which we are asked to project or estimate the average height of all the Chicago Bulls 1992/93 starting 5. Now, the sampling error is gotten from this sampling error of the mean. Now, since we are talking about a whole population, instead of x bar is going to be standard error or sampling error of mu, which is given as standard deviation, but in this case sigma, since we are considering population, divided by the root of the sample n multiplied by the root of capital N minus small n divided by capital N minus 1. Now, let us not forget, since we are using the same set of data, note that our mean is still given as summation of x divided by n, since we are talking of population, capital N, and this is still the same thing as 2.026 meters. We also know that our standard deviation of the population is also given as the sum of x minus, instead of x bar, this case is going to be mu squared divided by capital N, not n minus 1, because we are dealing with a population. And if you do the maths, you should have that your standard deviation is 0.0941 meters. Now, this implies that our standard error now, if we plug that, the standard error of the population mean is simply going to be our standard deviation, which is 0.0941 divided by the root of n, which is 5, multiplied by n. In this case, capital N is 5, small n is also 5, because we are given a population of 5 and we are sampling the whole 5 together. So, and here is going to be 5 minus 1. So you can quickly see that from here, 5 minus 5 is going to be 0 divided by 4, which is 0. So it makes the whole of this term 0. And if you multiply 0 by this term here, that gives you 0. So this implies that the standard error for the mean population in this case is going to be 0. And it is important to know that, and this is 0 because our n is 5, capital N is 5, and our small n is also 5. So in other words, we are sampling the whole people or items in the population. So in this case, the error is 0. But the reason why we have errors in the other ones is that out of all the population, we are simply taking a subset of the information, and that's why the error comes true. I hope this lecture is making sense to us, and we are seeing the importance of calculating all these parameters and statistic measures. Now let's quickly see how do you calculate what we call the sample size. Now it is important to know that whenever we carry out an experiment, we should be able to come up with a statistical measure or number to indicate how confident we are that if we repeat the experiment over and over, that we are certain for a number of percentage that we can get the same result. And that brings the issue of what we refer to as confidence interval or confidence level. And then from confidence interval and confidence level, in this last segment, we shall also see that given a population, how do we know the reasonable or optimal number of samples to be able to take out from this population in order to minimize our sampling error? Now, it is important to note that in the statistical sciences, or rather the social sciences, typical confidence interval in social sciences are 90% and 95%. That's typical confidence interval or confidence level. So if you are given a task or rather a statistical value with a confidence interval of 90, what it simply means is that I am 90% confidence that when I carried that particular experiment 100 times, 90% of the time, I'm going to get the same set of results. Now, the sampling size is calculated using the following formula. You can see the formula where that is n is equals to z alpha squared npq divided by e squared into n minus 1 plus z alpha squared pq. And all these terms in the formula have been neatly defined, where capital N refers to your population size, small e is your sampling error, which is a value that varies between 1 and 9, that is 0.001 to 0.009 is actually usually used, while z is a constant related to the confidence level, that's alpha, and can be used according to the following table. Of course, in most statistical table, you have the z alpha value versus the confidence level. So in other words, the confidence level of 75 corresponds to z alpha value of 1.5. of 90 corresponds to Z alpha value of 1.65, and of 95 corresponds to a Z alpha value of 1.96. Now let's see this simple calculation before we take our leave. It says, example, okay, this is an example of calculating P and Q. It says, initially, a pilot study of 150 voters is carried out. And from this survey, it is obtained that 60 of these voters have a favorable opinion. Now, how do we extract our P and Q? The P is simply trying to tell us the number of entities in our populations that have the desirable attributes. So in other words, 60 have a favorable opinion that the voting exercise or the election is going, for example, is going to go on peacefully and to be conclusive, while the remaining number have, an opposite opinion. Now, so you can see here, P refers to the proportion of those that have a favorable opinion. So in other words, P can be gotten as 60. We have 60 of those that have favorable opinion out of a total of 150 voters multiplied by 100. And if you do the math, that gives you 40%. And in fraction, that gives you 0.04. While in the case of Q is simply going to be in terms of percentage. Since we know a percentage from, say, 100 is going to be 100 minus 40, which gives us 60%. Or in decimal, that gives us 0.06. Now, it is important to note that P plus Q, the sum of P plus Q, is equals to 100 as a percentage, or 1 when you use a decimal, just like the way we have probability. Now let's see now how to calculate the sampling size. It says, calculate the sample size of a population of 500 items with a confidence level of 99%. And then we have P, the proportion, with the favorable or the required attribute as 0.5 for 99% confidence level, and Z is given as 2.58 and our margin of error as 0.05. Now, how do you calculate that? You simply make use of your formula, which was given as N is equals to Z squared alpha multiplied by capital N PQ divided by E squared N minus 1 plus Z alpha squared PQ. And all we need to do is just to plug in our values. Our Z alpha squared has been given as 2.58 squared multiplied by the sample size, which is capital N. We've been given that as 500 multiplied by P. We've been given as 0.5. We've been given as 0.5 multiplied by Q, also has been given as 0.5, and divided by E squared, which is also the error, which is 0.05 squared multiplied by capital N, which is 500 minus 1 plus 2.58 squared PQ multiplied by 0.5 multiplied by 0.5. And if you do the maths carefully, you should arrive at N is equals to 285.7, which can be, approximated as 286. So in other words, if you want to do a sampling out of these 500 items, in order for you to get an error margin that is very, very small, and to be able to get all your statistical, measure to be an accurate representation of your population, the entire 500 population, then it means you need to pick 286 samples out of this 500 in order to carry out your experiment or investigation. So that is that about populations and sampling and samples. And I hope that the information I've provided in this lecture has been very, very informative. But before I take my leave, permit me to share the last open class question before we go. The third open class question says, if the sample size are large from the population, then which error will contribute less error or errors? We have A, sampling error, B, non-sampling error, C, both A and B, D, none of the above. So simply answer all this question and upload them at the relevant section of your the learning management system for grading. I hope the information I've provided has been very informative and helpful. And I would like to thank you for watching. See you next week for the next class. Have a good night rest.